The universe is almost entirely empty. And that emptiness isn't an accident. It might be the whole point. Think about that for a second. We have spent centuries building telescopes, launching probes, training radio dishes at the sky, all to find something out there. Life, signals, a neighbor. And what we keep finding, over and over again, with almost offensive consistency, is nothing. Dead rock, frozen gas, radiation-soaked silence. But here's what nobody tells you in the headlines. The emptiness is statistically extraordinary. We're not talking about a universe that tried to make life and mostly failed. We're talking about a universe that built, by current count, at least 2 trillion galaxies, each containing hundreds of billions of stars, and populated almost all of it with worlds that are utterly, completely, magnificently lifeless. 2 trillion galaxies, hundreds of billions of stars each, and as far as we can confirm, one pale blue dot with anything moving on it. Either we are a miracle so improbable it strains the word miracle, or the emptiness is doing something we haven't figured out yet. Because if you keep watching, you're going to realize the empty planets aren't a failure of the universe. They might be its most important feature. Picture a Saturday morning. You're a kid, maybe 8 years old, and someone hands you a bag of marbles. 200 marbles, all different colors, and you pour them onto the kitchen floor. They scatter everywhere, under the refrigerator, behind the cabinet, across the tile, and you spend the next 10 minutes on your hands and knees collecting them. Now imagine you find 199 of them easily. But number 200, you search and search. You check every corner. You lie flat on the cold floor and peer under every appliance. Nothing. And then, finally, wedged in the single most unlikely gap between the dishwasher and the wall, you find it. One marble, hidden. The only one that mattered enough to hide. That's the shape of our universe. 200 marbles, and we're the one that somehow ended up in the most improbable spot. But here's what most people never ask themselves when they think about the universe. Why are there 200 marbles at all? If all you needed was one marble with life on it, if life was the goal, why build a universe of such almost incomprehensible scale to produce it? Why not a smaller kitchen floor? Why not 10 marbles? Why not one? The sheer wastefulness of it, that's what stops serious physicists in their tracks. Carl Sagan once said, "The universe is not required to be in perfect harmony with human ambition." That's generous, because what the universe seems to be saying is something more radical. It doesn't care about efficiency. It built a structure that stretches 93 billion light-years across, and then populated most of it with rocks no one will ever visit. And sitting in your kitchen pouring coffee, you are somehow the marble that ended up in the gap. That's either the most beautiful thing in physics or the most terrifying. Possibly both. Every generation of scientists has asked some version of the same question: are we alone? It's a good question. It's a thrilling question. It launched a field, astrobiology, and filled 100 science fiction novels and kept radio telescopes pointing at distant stars for decades. Are we alone? Is there anyone out there? But there's a deeper question hiding underneath that one. A quieter question. One that doesn't get asked on magazine covers. Not, are we alone? But, why is it even a question? Why would a universe that supposedly made life do such an extraordinary job of making everything else? Why would the same physical laws that assembled amino acids in a warm ocean also build gas giants with no surface to stand on, moons of methane, rogue planets drifting in frozen darkness between galaxies, billions upon billions of objects that are structurally incapable of supporting anything like us? Nobody stops to ask that question. We assume the barren planets are just background, filler, the universe's way of taking up space while it got on with the real work of making life somewhere interesting. But what if they're not filler? What if the billions of empty planets are the thing and we're the accident? Or, And this is the idea that keeps cosmologists and physicists awake at genuinely odd hours. What if the emptiness and the life are inseparably connected? What if you cannot have one without the other? The real question, the one that breaks everything, is this: could life exist in a universe that wasn't almost entirely empty? Because the answer, it turns out, is almost certainly no. And the reason why will change the way you look at the night sky forever. Open any introductory astronomy textbook and you'll find a comfortable answer to the rarity of life. It goes something like this. Life requires very specific conditions. You need liquid water, which means you need the right temperature, which means you need to be the right distance from the right kind of star. You need an atmosphere stable enough to protect you from radiation, but thin enough to allow sunlight through. You need a planetary magnetic field. You need a large neighboring planet like Jupiter to vacuum up rogue asteroids before they sterilize your surface. You need geological activity to recycle nutrients. You need time, billions of years of it, for chemistry to slowly assemble itself into biology. The chances of all of those conditions meeting in one place? Slim, very slim. So the textbook shrugs and says, the universe is mostly empty because the conditions for life are rare. Simple as that. Most planets don't hit the checklist, so most planets stay dead. This is called the rare Earth hypothesis in its modern form. The idea that complex multicellular life requires such a freakishly specific combination of circumstances that it may have happened only once, or nearly once, in the observable universe. It's a satisfying explanation, clean, logical. It fits on a slide in a lecture, and it answers the question without making anyone too uncomfortable. But here's the part the textbook skips. It explains why life is rare. It doesn't explain why the universe is so extravagantly, almost deliberately, large. If rare conditions are the whole story, if we're just an improbable roll of the dice, why are there so many dice? Why build a cosmos of 2 trillion galaxies and hundreds of billions of stars per galaxy to roll a lottery with those odds? The rare Earth hypothesis tells us how unlikely we are. It says almost nothing about why the universe built such an enormous stage for such an improbable performance. So the textbook says life is rare because the conditions are rare. Seems fair. But the universe does something far stranger. It turns out the emptiness, the barrenness, the billions of dead rocks isn't a side effect of the conditions that make life possible. The emptiness is a requirement for them. Here's where we have to talk about physics, real physics, not the metaphor, the actual structure of the universe. In 1998, 2 independent teams of astronomers were doing something fairly routine, measuring how fast the universe's expansion was slowing down. Because obviously it was slowing down. Gravity pulls things together. The Big Bang sent everything flying apart, but gravity should be winning the tug-of-war by now, decelerating the expansion like a ball thrown upward, eventually losing its momentum. Except it wasn't slowing down. The universe's expansion was accelerating, getting faster, driven by something we can't see, can't measure directly, and don't fully understand. Something we've given the embarrassingly vague placeholder name, dark energy. This won 3 physicists the Nobel Prize in 2011. And what it revealed is astonishing. The vast empty space between galaxies is not passive. It has energy. And that energy is not stable. Or rather, its stability is one of the most finely tuned numbers in all of physics. The value of dark energy, what physicists call the cosmological constant, is unimaginably small, about 10 to the power of minus 122 in natural units. If it were slightly larger, even by 1 part in 10 to the power of 120, the universe would have expanded so fast after the Big Bang that matter would have scattered before gravity could pull any of it into stars and planets. No galaxies, no chemistry, no life. If it were slightly smaller, even by the same margin, the universe would have collapsed back on itself within the first second. No time for anything to form. The emptiness, in other words, is calibrated. The billions of dead planets exist because the same cosmic vacuum that makes empty space empty is holding the entire structure of existence at the precise tension required for anything to exist at all. Let's try something. Step out of yourself for a moment. You are not a human being on a planet. You are a physicist with godlike powers and a blank canvas. Your task is simple. Build a universe capable of producing life. You're not constrained by anything. Build it however you like. Your first instinct might be to be efficient. Why waste material? Why build hundreds of billions of galaxies if all you need is one? So you start small, a modest universe, a single galaxy, a few 100 billion stars, maybe a handful of planets orbiting each one. You run the simulation. Immediately things go wrong. A universe that small has different gravitational dynamics. The background energy density is different. The rate at which the universe expands and cools in those first microseconds. The precise window during which protons and neutrons fused into the first atomic nuclei would be altered. Your small universe cools too quickly or not quickly enough. The ratios of hydrogen to helium come out wrong. Stars of the right kind, long-burning, stable, middle-aged stars like our Sun, don't form in sufficient quantities. You try again, bigger, then bigger again, and slowly you discover something maddening. Every time you make the universe smaller, you lose something critical. Every time you strip away some of the emptiness, some of the dead distance, some of the sterile light years between galaxies, something goes wrong with the physics. The expansion rate, the density fluctuations that seed galaxy formation, the amount of time the universe has before dark energy drives all galaxies beyond the cosmological horizon, and every civilization, if any existed, would look up and see only darkness. You can't seem to build a small universe that produces life. The life and the emptiness are locked together. They come as a package. You stop. You look at your blank canvas, and you realize the only universe that can contain one living planet must also contain trillions of dead ones. Not as a flaw, as a feature. Because what that means, what that really means for why you exist, is something that physics is only now beginning to put into words. Think about baking bread. If you want the bread to rise, you need yeast to produce gas bubbles inside the dough. But here's the thing. The yeast doesn't target the final loaf. It fills all the dough uniformly, and most of the dough just becomes bread. Only a small fraction of the volume is bubbles. The bubbles are the product. The bread is the necessary medium. Life might be like the bubbles, and the universe, all of it, the trillions of dead planets and empty light years and barren moons, might be the bread. The medium without which no bubble could form or persist. The universe isn't mostly empty despite producing life. It's mostly empty in order to be the kind of structure where life is even theoretically possible. There's a relationship physicists call the flatness problem. The observable universe is geometrically flat, meaning its total energy density sits almost exactly at a specific critical value, denoted omega omega. Measurements put omega at 1.0002, plus or minus 0.0002, essentially exactly 1. For omega to be so close to 1 today, almost 14 billion years after the Big Bang, it must have been almost inconceivably closer to 1 in the first fractions of a second of existence. Physicists calculate that in the first second, omega differed from 1 by less than 1 part in 10 to the power of 60. What that number means in human terms, the universe's density was balanced so precisely at its birth that the margin of error would be equivalent to weighing the entire planet Earth and being off by less than 1 atom. A universe that isn't flat doesn't hang around long enough for stars to form. Flatness, that extraordinary precision, is what gives you the billions of years of stable expansion that chemistry and biology require. And what this tells us about reality is almost too large to look at directly. It says that life is not an accident embedded in an indifferent universe. Life is an outcome, a very specific, very rare outcome of a universe whose physical parameters are set with almost surgical precision. And those parameters, the ones that make life possible, cannot be unpacked from the ones that make the universe vast and mostly empty. The emptiness is not waste, it is the scaffold. Let's move through scales, from the impossibly small to the incomprehensibly large, and watch the same principle operate everywhere. Inside a single hydrogen atom, the most abundant atom in the universe, there is almost nothing. The nucleus sits at the center, and the electron orbits at a distance that, to scale, would place it roughly a mile away if the nucleus were the size of a basketball. A hydrogen atom is, by volume, more than 99.99999999999% empty space. And yet that emptiness is not nothing. That space, the quantum vacuum between the electron and nucleus, is what gives atoms their size, their chemical behavior, their ability to bond into molecules. Compress that space and chemistry collapses. No molecules, no water, no proteins, no life. Step up, you. Your body is made of roughly 7 times 10 to the 27th power atoms. And if you removed all the empty space from those atoms, packed the actual nuclear and electronic matter together, the physical matter of your body would fit inside a cube about 1,000th the width of a human hair. You are almost entirely empty space, reading about empty space, in an almost entirely empty universe. Our solar system contains 8 planets, at least 5 dwarf planets, hundreds of moons, and a vast asteroid belt. The total mass of everything in the solar system that isn't the Sun, every planet, moon, asteroid, and comet combined, adds up to less than 0.2% of the solar system's total mass. The overwhelming majority of the volume of our solar system is unoccupied. The distances between planets are staggering, even on a local scale. Zoom out further. The observable universe is roughly 93 billion light-years across. All the matter in it, stars, planets, gas, dust, dark matter, constitutes only about 5% of its total energy content. The rest is dark energy and dark matter, the latter invisible and detectable only by its gravitational effects. The average density of the universe is equivalent to roughly 6 hydrogen atoms per cubic meter. To put that in perspective, the best vacuum we can create in a laboratory on Earth still contains millions of atoms per cubic meter. The universe is emptier than anything we can manufacture, and across every scale, atomic, human, planetary, cosmic, the same principle holds. The emptiness is structurally necessary. Remove it, and the whole thing falls apart. There's a concept in physics called the anthropic principle. It's been argued about, reframed, misrepresented, and occasionally used as an excuse not to think harder. But in its most honest form, it says something genuinely profound. It says, the universe we observe must be compatible with the existence of observers. Which sounds circular at first. Of course we see a universe we can exist in, because we couldn't see one we couldn't exist in. Fine. But think about what that actually means. We don't just happen to live in a universe with the right laws. We live in a universe where the laws are calibrated to better than 1 part in 10 to the power of 120 in multiple independent parameters. The cosmological constant, the flatness, the ratio of electromagnetic to gravitational force, the mass of the electron, the strong nuclear force constant. Change any of them slightly and no stars form, or stars explode immediately, or atoms don't hold together, or the universe collapses in a nanosecond. Those parameters don't just allow life, they require a universe of the shape and size we see. A universe with enough time for heavy elements to be forged in stellar cores, scattered by supernovae, gathered into new solar systems, and finally assembled by slow geological and biological processes into a creature capable of asking this question. That process, from Big Bang to you sitting here, takes roughly 13.8 billion years. It requires a universe old enough, stable enough, and large enough to have done all of that work. And here's the moment the magic trick gets explained. The empty planets aren't a failure of intent. They aren't waste. They are the evidence, the physical signature, that the universe had enough time and space and material to run the entire lottery. Every dead world is a ticket that didn't win. But the existence of billions of losing tickets is proof that the lottery ran long enough and at large enough scale for a winner to exist at all. We are not alone in a universe of empty planets. We are the inevitable result of a universe that had to be built at exactly this scale to produce anything at all. But let's sit with the discomfort for a moment. Because the physics, as beautiful as it is, doesn't actually close all the loops. Even if we accept that the universe had to be this large, this empty, this old, this precisely calibrated, we haven't answered the question underneath the question. Why does it exist at all? The fine-tuning we've described, those parameters set to 1 part in 10 to the power of 120, could be explained in several ways. Maybe there's a multiverse, an infinite ensemble of universes, each with different physical laws, and we simply inhabit the one that happened to be compatible with our existence. In an infinite multiverse, a universe like ours is not miraculous, it's inevitable. Somewhere in the ensemble, every configuration gets tried. But that raises its own question. Where does the multiverse come from? What determined the rules of the mechanism that generates universes? Alternatively, maybe the laws of physics as we know them are not arbitrary. Maybe they're necessary. Maybe they're the only consistent set of laws that could describe a universe with internal logic. Maybe the universe couldn't have been any other way, not because of a designer, but because existence itself has a shape, and we're discovering it. Or maybe, and this is the possibility that neither comforts nor disturbs, but simply astonishes, maybe we're asking the wrong question entirely. Maybe why is a human invention, a category we impose on a universe that preceded us by 13.8 billion years and will outlast us by incomprehensibly more. Every empty planet is a question we haven't answered. Every barren moon orbiting a distant gas giant is a reminder that the universe operates on rules we're still learning to read. And the deepest unanswered question the physics of emptiness raises is not whether we're alone. It's this. Does a universe need a reason to exist? There is a planet, no one has named it. No probe has visited it. No telescope has photographed it clearly, orbiting a dim star near the edge of a galaxy that is roughly 400 million light-years from Earth. It is a rocky planet, slightly larger than Earth. It has a thin atmosphere of carbon dioxide and nitrogen. It orbits in what astronomers would call the habitable zone of its star. And it is completely, utterly lifeless. No bacteria, no spores, no chemical precursor reaching the crucial threshold. Just rock and wind and the occasional impact crater slowly being smoothed over by geological time. That planet has existed for approximately 4 billion years. It will continue to exist for another 5 billion before its star expands and consumes it. In 9 billion years of existence, nothing on its surface will ever move with intent. Nothing will eat. Nothing will wonder. Nothing will look up. It is not a tragedy. It is just what most of the universe is. But here's the thing. That planet, that specific, silent, empty world, is part of the same physical system as you. The same laws govern its atoms and yours. The same cosmic expansion that is slowly cooling its star also governs the dark energy threading through the space between your neurons. It is empty so that somewhere, across the unthinkable distances, the math could work out. The universe didn't make billions of empty planets instead of making you. It made billions of empty planets in order to make you possible. You are not proof that the universe is generous. You are proof that it is precise. The universe is almost entirely empty, and that emptiness isn't an accident. It might be the whole point.